think we're ready to go. All right. What are those?
The green things are the leafy cells, and then the red, that's a nucleus.
Good, good.
Okay.
All right, so this particular image here shows us the synapse, right? You guys remember the synapse? What's the synapse? We define the synapse as what?
They're the things in between different neurons where they tell the information to the next one.
Exactly. So it's a fluid-filled gap is what we're going to say. Synapse, synaptic cleft. And so it says presynaptic terminus on this side. So this would actually be an axon terminal button. And this right here would be, what's the receiving part of the neuron, Mr. Goodman?
It's like a dendrite.
The dendrites, yeah. So most of this would be dendrites. There are receptor sites on dendrites, and there's also receptor sites on the soma as well, okay? But I want you to think about the dendrites mostly being in the receivers, but sometimes it can go directly into the soma because there are receptor sites there as well. See these right here, the gold dots in between? What would that be? What would it be? That's your neurotransmitters. That's your dopamine, that's your norepinephrine, your acetylcholine, serotonin that we mentioned in the article beforehand. Sound good? So when the neuron fires, it's going to spew it out into the synapse, and then it's going to be received by postsynaptic terminus, dendrites, and axons. Really, what it is. Okay. All right. So we're going to go through this, and it's going to be a little bit repetitious here for a moment on some of the notes, repeating on how this information is transferred from one neuron to the next. Okay. I think we've got a good start though. So what causes the intensity of our emotions? So sometimes I'm kind of happy, and then other times I'm like really, really happy. You know, I was talking to Mr. Prainer the other day. I went to listen to a comedian one time when I was in college, and after we got done, you know, that night my face hurt because I smiled so much. I laughed so hard that night, right? So what caused my happiness and laughter and enjoyment to be so much higher in that situation than others, besides apart from the stimulus? You know, physiologically, we're thinking about the number of neurons that are firing. Okay, so it's a combination of two things. The number of neurons firing, you had a greater number that particular night, and then the rate at which they fired as well. It was a faster rate. Okay, so keep those two things in mind. The intensity of our emotions is going to be contingent upon the number of neurons firing and the rate at which they fire. Okay, and then of course, we think about the myelin sheath and the nodes of Ranvier. I used this analogy the other day of the walkways in airports as well to speed up those neuronal transmissions. The rate at which they travel through our body, 224, I'm not sure if this is meters or miles. I think I may have misprinted this, so you may have to go back and check in your text whether it's meters or miles. Either way, it's extremely fast, right, in order for that neuronal transmission to take place. All right, so we talked about the nodes of Ranvier in the myelin sheath. I mentioned Parkinson's disease, deterioration of the nodes of Ranvier, leads to MS. Anybody ever heard MS before? Multiple sclerosis, right? I had an uncle that had MS, and I was young at the time when he was going through his issues. He ended up passing away. He was only in his 30s, I believe, at the time. He was on bed rest all the time whenever we went to visit the family or his family that way. So very detrimental to our health whenever you have the deterioration of the nodes of Ranvier. So neurotransmitters, again, they're chemical substances that transmit messages between the neurons. We've already started listing a couple with our article that we read through. We want to think about the synaptic transmission just a little bit more here as we go through. Inside the axon terminals, you have these synaptic vesicles. Of all this, I just want you to write down synaptic vesicles real quick. And maybe out to the side of synaptic vesicles, write little bladders, because sometimes that's what they're called. So we haven't really emphasized this yet, but when the neurotransmitters are passing through the neuron, it's not like they're out there singularly by themselves. They're kind of grouped together in what they call these little bladders or synaptic vesicles. And then eventually it's like a family of neurotransmitters, and then it'll pass through the axon down to the axon terminal bud, and then it'll fuse to the wall, and then when the neuron fires, then it'll spew that family of neurotransmitters out to the synapse. Sound good? So you're not like by yourself as you're passing through the neuron. Okay. The guy that came up with this was this guy named Otto Lowy. We don't necessarily have a test question on him, just some interesting facts there. So here you can see these are the synaptic vesicles, the little bladders. Sound good? So your neurotransmitters would be one green dot here, and as it's going through, this would be your axon terminal bud here. As it's going through, you can see that they're grouped together, and then it's going to fuse to the membrane of your axon terminal bud, and then when the neuron fires, it's going to expel the neurotransmitters out into the synaptic cleft, and then here's their receptor sites, and that would be on your dendrites or on your soma. Okay? Again, don't write this down, it's just repetitious. When the neuron fires, the action potential moves to the end of the axon terminal, triggers the release of neurotransmitters from the synaptic vesicles, which flow into the synaptic cleft. Okay? The neurotransmitters cross the synaptic cleft and attach themselves to the receptor site of the cell body, dendrites to the receiving neuron. Again, there's your receptor sites. One key thing, kind of jumping ahead here maybe a little bit with one of the slides we're going to look at a little bit later. These neurotransmitters and the receptor sites, they have shapes to it. Okay? And certain neurotransmitters will only match up with certain receptor sites. Okay? And I think of it kind of like Preston and Duke, they got this game where they had the shapes like triangles and squares and circles and things like that, and they all fall out on the ground. And then they got this box where they got to put it inside of it, right? And if they can't match it up, then it doesn't go into the right spot, right? It never makes it in. Okay, same thing, right, with the neurotransmitters. If they don't have the right shape, then they're never going to match up with the receptor site and be received by the receiving neuron. Okay, so think of it like that way. Okay. Now, when these neurotransmitters get to the receiving neuron, they're going to inform the nucleus there, once it gets down to the soma, whether they need to fire or not, okay, or what type of neurotransmitters they need to produce then thereafter. So that's how they communicate with one another, and information is transferred from one neuron to the next. All right. Again, I got videos in there so that you can go back and look at them on your own and get some new, different insights. These receptor sites, they're made of protein molecules that are on the dendrites or on the soma. And like I said before, they only receive neurotransmitters of a particular shape. So you can think of that analogy that I shared with you of the shapes with the children's toy, or you can think of it kind of like a lock and a key kind of analogy as well. Now, one thing that I want you to keep in mind is a lot of drugs like alcohol or drugs that we would say illegal drugs, right? Narcotics. The neurotransmitters that are produced by those drugs are kind of like a skeleton key, right? They can fit into almost any of those receptor sites, and that's what makes them so dangerous, okay? Because they can greatly influence and affect our behavior that way. Sound good? So I always thought that was interesting information there. So some neurotransmitters are a little bit more optimal in being received by the dendrites and the soma than others. Okay? So there's two categories of neurotransmitters. You have excitatory neurotransmitters and you have inhibitory neurotransmitters. Right? And essentially, what I want you to know is, what do they do? Excitatory neurotransmitters, what do you think they're going to do to the next neuron? Are they going to make them fire, or are they going to make them slow down and not fire? It's excitatory. You're going to make them fire. Right? So it speeds up the neuronal transmission, because sometimes we need that. But then there are other neurotransmitters that act as inhibitory neurotransmitters, and they slow things down. And sometimes we need that too, because if we get ourselves going too fast, it can be detrimental to our health. We could actually kill ourselves, right? I'll give you an example. Acetylcholine, right? The one we mentioned associated with Alzheimer's, lack of production leads to Alzheimer's. Well, it's actually also a neurotransmitter that helps for motor functions and movement. So say that you're late for class, and in the morning, you show up and you're that person that has to park all the way on the other side of the football field, right? And you got a minute to get to class. So what do? You take off running. You don't have any tardies left, right? You know that there's going to be consequences this time. And so your acetylcholine acts as an excitatory neurotransmitter for all your muscles. So it gets you going. So thank goodness for that. Otherwise, you're obviously going to be late. Okay, so you get to class. But what you need to do is you need to calm yourself back down, though, right? Because you got yourself going so fast. And your acetylcholine actually acts as an excitatory neurotransmitter for your muscles, but it acts as an inhibitory neurotransmitter for your heart, right? Because think about it this way. If it didn't act as an inhibitory neurotransmitter for your heart, what would happen to your heart? It would blow up. It would explode. You would die. So thank goodness it works that way, both in excitatory and inhibitory. Okay, so some are excitatory neurotransmitters, some are inhibitory. Another analogy, think about cooking, plastic rubber handles. Those are inhibitory type of, it inhibits the conductance of heat. And then the copper bottoms, that would be excitatory, it heats things up pretty fast. Okay? We already talked about that. Where do they come from? The neurotransmitters, they come from the cell body. Two other ways in which you can accumulate neurotransmitters. When they're in the synaptic cleft, sometimes they're broken down into the chemical substances, and then they're reabsorbed by the axon terminal buds. Sound good? So that happens quite a bit as well. And then there's this last scenario, which is kind of like this, right? It doesn't happen very often. Test question right here. Maybe we'll put an asterisk next to it. But when the neurotransmitters are out in the synapse, or the synaptic cleft, and they're whole, the axon terminal bud will just suck it right back up, whole as well, and then it'll reuse it. Okay? So again, that doesn't happen all that often, but that process is called re-up. Sound good? Let's see if we can knock out a couple of these neurotransmitters before we run out of time today. There are 75 or more neurotransmitters. We're not going to go through all of them. We're going to go through just a few of them. Sound good? But 75 chemical substances that go throughout our body that could be classified as neurotransmitters. Sometimes they're classified as hormones and other type of things, but 75 altogether. Okay? We mentioned acetylcholine, right? So you should be pretty familiar with this one. It's both an excitatory and inhibitory. Excitatory effect on our muscle fibers so that we can move, and then an inhibitory effect on our heart, like we mentioned before. Just think about the scenario. You're late to class, you're running. Thank goodness your acetylcholine is going to allow you to move, right? And then also keep you from your heart exploding, jumping out of your chest like this guy, okay? Have you guys ever heard of, I'm not sure if I got that, Pure Air? You guys ever heard of poison darts from the Amazonian rainforest before? Right? What it does is it blocks acetylcholine. So your neurons can't acquire it anymore, can't take it in. And so what does that do to your muscles? You can't move. You become paralyzed. You become paralyzed. If you don't have treatment really quickly, you're going to die that way. Poison darts. Okay. Another category of neurotransmitters, or a category of neurotransmitters, kind of mentioned these in our article, would be the monoamines. You got dopamine, norepinephrine, epinephrine, and serotonin. Okay? And remember we said dopamine is about alertness, right, and attention. Norepinephrine and epinephrine, alertness and attention as well. And it's sometimes associated with eating habits, hunger, thirst, those type of things. Somewhat sexual behavior here as well. But dopamine is the one I want you to think about with alertness and attention. Serotonin, again, what would that be associated with? Gotta eat bread. But what else? Calm. Feel good. We're going to say feel good neurotransmitter. We love serotonin. Okay? We want serotonin. We're really concerned if we don't have enough serotonin. Okay? And it can be created by other things besides food, like, relationships. Authentic relationships and communication with other people can help your body produce serotonin. Sound good? when we lack those relationships, the authenticity of relationships, when I'm just on my cell phone and I'm just texting everybody and on social media, that's not an authentic relationship. Consequently, my body doesn't produce the serotonin like it normally would if I'm actually having a face-to-face conversation and I develop this warm, fuzzy feeling type of relationship with other people. Okay? That's where my serotonin is produced. Okay? So that's one problem with young people today. We have issues with depression and anxiety because the relationships are just different today than what they were in past generations. The most common excitatory neurotransmitter, good test question here, is glutamate. 40% of the neurons in the brain actually produce glutamate. Most common inhibitory neurotransmitter, slow things down, is GABA. It controls human anxiety. You may want to write out to the side. It's associated with the consumption of alcohol. All right, so if it controls anxiety, so if I consume alcohol, I increase my production of GABA. That takes my anxiety away. Has everybody got that? So that's why a lot of times alcohol is associated with social settings, because people have anxiety when it comes to going up and having a conversation with somebody they never had a conversation with before. So they got to have something to calm them down a little bit, and that's because of the inhibitory neurotransmitter of GABA. You drink it to the extreme, and then you suppress all inhibitions, and then you end up doing things that you later on regret a little bit later on. Sound good? All right, we'll wrap things up on neurotransmitters on Monday. Make sure we clarify any type of misconceptions that we have, and then we'll move on. Appreciate your attention today. Ms. White, you want to get the lights for me, please? Thank you.
Thanks for taking us down to watch.
Yep.
Really sleepy last night.